So we have learned that given a scalar product, the formula here provides us with a norm. Let's label this formula with a little star for later reference, and let's ask ourselves whether the same situation works the other way around. So conversely, given a norm, can you always find a scalar product such that star holds ? Okay, that's an interesting question because it's somehow it's turning the story upside down. Because before we said whenever you have a scalar product, then you have a norm, and hence normed spaces or spaces with a scalar product are a subset of the set of all normed spaces. Now, if this would also work the other way around, then these would be the same, and then Hilbert spaces and Banach spaces would be the same, which would probably be strange. So why would we need different names for one and the same thing? So probably the answer is no, but let's find out ourselves. So let's just reformulate this question a little bit. Instead of saying we are given a norm, and in the end we want star to hold, we could say given x comma x for all x's, because if we have x comma x, then we have the root of x comma x, and that's what the norm should be. Can we give a formula for x comma y for all x and y in x ? When someone asks you such a question, it sometimes helps to look at the toy example. Let's say x is just a space of all real numbers with the usual structure. Scalar product is just product. Then our question is, given squares for all real numbers x, how can we compute products x times y, where x and y are no longer the same, probably? So how can you compute products if the only thing you have is squares? And okay, let's be fair, in our real numbers we also have addition. We have plus and minus, of course, and we have little alpha times, which in this case is, of course, to be honest, already x times y. And the key in this case is given by the binomial formulas. So x plus or minus y, and then in brackets squares is x squared plus or minus 2xy plus y squared. From this you can conclude two things. If you add x plus y squared and x minus y squared, then the squares will add up and the mixed terms will cancel. So you get 2x squared plus 2y squared. Whereas if you subtract them from each other, then the squares will cancel and the mixed terms will add up, giving you 4 times xy. Okay, and the red formula provides us with the answer. So if you only have squares and plus and minus, how can you compute x times y? Well, you use this, and in the end you have to divide by 4. But that's what I mean by we still have this alpha times. So inspired by this little toy example, let's go back to the general case and try norms and scalar products. So let's somehow copy the red line and get back to norms. So we just look at x plus y and x minus y, their norms, and then squares. And if we rewrite this as scalar products, then we have x plus y, comma x plus y, and subtract x minus y, comma x minus y. And then when you multiply everything out, you get this, where the green term is just what you get if you expand that green part, and the black term is what you get when you expand that black scalar product. Okay, now let's simplify. We have cancellation here and here, and again here and here, and what remains are the mixed terms. So if you write this out, you get 2 times x comma y from here, note the minus sign in front, and 2 times y comma x coming from here. And of course you can simplify that into 2 times x comma y plus 2 times x comma y complex conjugate, or just in short, 4 times the real part of the complex number, possibly complex number, x comma y. So if your vector space X is real, then that computation essentially seals the deal, because you just divide by 4, and then you have not just the real part, but all of your scalar product X comma y. In case it's a complex vector space, you still need the imaginary part. And to get your imaginary part, you essentially repeat the same calculation, only getting a little I into it in front of the y. So let's look at x plus I times y norm squared minus x minus I times y norm squared. And by going through the very same calculations, you end up with 4 times the imaginary part of x comma y. So if we just abbreviate this term here by little a and this term here by little b, then we can summarize as follows. Your scalar product x comma y is given by the blue expression a divided by 4 if you're in a real vector space, and it's given by a divided by 4 plus I times b divided by 4 if you're in a complex vector space, right? So let me just remind you where these terms are coming from. So a is 4 times the real part of what you need. So if you divide a by 4, then you get the real part, which in the case of a real vector space is already everything, and in the case of a complex vector space is only the real part. So the imaginary part comes here from b divided by that 4, and of course do not forget the I in front. So it seems that indeed from just looking at norms we can always compute scalar products, but the sentence is not quite finished yet. So this is a scalar product on X if, and here's the condition. And to see this condition, we follow up our computations up to our toy example, where we also saw this first equation, and that one is not using scalar products at all, it's just using squares. So this should also be the case, and indeed it turns out if this is the case, then you are in the situation that you want, that by just computing norms you can compute a scalar product. So we have to write down that blue equation again, and here it is. So if you compare, if you take x plus y norm squared and x minus y norm squared, and this time not subtract them like we did in A, but rather than add them, then the mixed terms cancel and we get 2 times norm of x squared and 2 times norm of y squared, and that's how you can check whether or not your norm allows for a scalar product. This equation here is called the parallelogram identity. Let me just write down the name. Parallelogram identity and usually abbreviated by PI. It's called parallelogram identity because if you look at vectors x and y and you just draw this little parallelogram, then the one diagonal in it is just x plus y, and the other diagonal is just given by the vector x minus y. And all this parallelogram identity is saying that when you take the length of the green diagonal and the length of the black diagonal squared, add them, you get 2 times the length of the blue side squared plus 2 times the length of the red side squared, and apparently that holds in all parallelograms, and well, hence its name after that. Okay, so let's summarize again. So this is apparently a very important identity. It even has its own name. And what did we say? We said that this formula gives you a scalar product just purely based on norms, because little a and little b are given by norms, if the parallelogram identity holds for your particular norm. So your norm has its own scalar product if it's subject to the parallelogram identity. This is not easy to see. This is we didn't show this yet. This is in fact its own theorem, and we will not give the proof here. So the proof consists in checking whether this expression here is subject to our properties S1 to S4 of the scalar product. And we didn't do that, but it's possible to do. The other thing one can say is that if you start from a scalar product, then your induced norm is always subject to the parallelogram identity, and that computation is done just like the one we did in our baby case. So here you follow the same argument, and instead of squares of numbers, you take squares of norms of vectors and compute them, well, like we did in this stuff. And you will arrive at this conclusion very easily. Okay. So let's summarize what we just said in a little corollary that follows from the theorem. So a normed space x plus alpha times, and of course a norm has a scalar product that is compatible with the norm via star. So remember, star was that the norm is just given by scalar product of an element with itself and then taking the root, if and only if the norm is subject to the parallelogram identity. Okay, very important corollary, and we will try that for different examples.